Hi, and welcome to lesson 4.4, Prove Triangles Congruent by SAS and HL. So I'll tell you the SAS stands for side, angle, side. Last lesson we looked at side, side, side congruence postulate. As you can see right below, this time we'll be looking at side, angle, side. And then the HL stands for hypotenuse and leg, which is a special right triangle relationship which we'll explore midway through this lesson. So the first thing we're going to look at is postulate 20, the side angle side congruence postulate. So again, all these relate just to triangles. So in this postulate, it says if two sides and the included angle of one triangle. So let's first make sense of two sides and the included angle. The two sides, when they say included angle, that would be the angle where those two sides meet. So if I'm looking at side SR and side TR, my included angle is angle R, or angle SRT, where those two sides, SR and TR, meet. So if I was looking at RT and ST, my included angle where they meet would be angle T. So let's go back to the postulate. If two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then those two triangles are congruent. So in that case, we would need two sides of equal length and one angle measure of the same degrees. So if we're looking at the example 1 here, we know that RS is congruent to UV. They both have the double hash mark. Angle R with the single arc is congruent to angle U with the single arc. And then side RT with the single hash mark is congruent to side UW with the single hash mark. So now matching up corresponding pieces, R corresponds with U, S with V, T with W. So if I name the first one RST, the second one would have to be named UVW. Now, if we move to example 2, they tell us in this diagram ABC is a rectangle. They're asking what conclusion can we come to, or what can we conclude about triangle ABC and triangle CDA? So first off, the term rectangle tells me quite a few things. The definition of a rectangle is that opposite sides are parallel and congruent to each other, and that all the corners or all the vertices are right angles. So if I go in here, I know angle A up in the left, whole thing's a right angle. C in the bottom's a right angle. I know side AB is both parallel and congruent to side CD, and then side AD is parallel and congruent to side BC. So right away, I know side AD is congruent to BC. I also know angle D is congruent to angle B. Both are right angles. And then we also know that AB was congruent to DC. So AD and DC meet at the included angle of D. AB and CD meet at the included angle of B. So I don't even care that side AC is congruent to itself. Unless I was using side, 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 then that would work. But also with side angle side, we can say that triangle ABC is congruent to triangle CDA because we have one side, the included angle, and then the other side that are congruent to each other. Now we get to that hypotenuse leg idea. So right triangles, we know are special triangles with one right angle. The two sides adjacent to the right angle are called legs. So the two sides that meet at the right angle are leg 1 and leg 2, or our two legs of the right triangle. The side that's opposite the right angle is always the hypotenuse. So the hypotenuse is the side opposite your right angle in a right triangle. The legs are the two sides adjacent to the right angle, or the two sides that meet at the right angle. So the reason these two terms are important is in theorem 4.5, it's known as the hypotenuse leg congruence theorem. So this one's not a postulate, but a theorem. Same concept. In this case, we're specific to just right triangles. If it's not a right triangle, we don't have a hypotenuse to speak of. So anytime you're going to use hypotenuse leg, it has to be a right triangle. So theorem 4.5 reads, if the hypotenuse and one leg of a right triangle are congruent to the hypotenuse and one leg of a second right triangle, then the two triangles are congruent. So if the hypotenuse and one leg are congruent to the hypotenuse and another leg, those two triangles are congruent. So if I look at triangle ABC here and DEF, both are right triangles. So our hypotenuse in ABC is the side opposite the right angle, which is AB. Hypotenuse in DEF would be side DE. So you can tell from the two hash marks, those are congruent. Then side DF is one of my legs. Side AC is a leg. Those are congruent to each other. So we have a hypotenuse and a leg that are congruent. So those two triangles are congruent. And then we match up corresponding vertices. So A with D, B with E, C with F. So ABC is congruent to triangle DEF. So now we're going to look at a proof based on that idea of hypotenuse leg. So complete the following proof. Obviously, they filled in some of the statements and reasons for us. So let's look at the given info. They told us side AC, or segment AC, is congruent to segment EC. So A to C here, congruent to E to C here. They marked it with the congruent hash mark. AB is perpendicular to BD. So if AB is perpendicular to BD, that means side AB and BD meet at a 90-degree angle. So angle B is a right angle. ED, perpendicular to BD, ED and BD also meet at a right angle. So now I know I have a right triangle over here and a right triangle over here. Finally, they tell us AC is a bisector of BD. So that means AC meets BD at its midpoint. To bisect something, you're meeting it at its midpoint and cutting it into two equal parts. So that would also tell me that BC is equal to CD, or congruent to each other. So I put the double hash mark in there to let me know those two sides are congruent to each other. So even before I looked at the proof, I just took the given info and marked what I knew on my diagram to help me. I know my final step is to prove triangle ABC is congruent to triangle EDC. So let's look at the proof they laid out. They started with two statements that are both from the given. So our first two reasons are given. Then they told us B and D are blank from the definition of perpendicular lines. Well, like we noticed here, B and D are right angles. So angles B and D are right angles, or 90 degrees, from the definition of perpendicular lines. Then we could state that triangle ABC and triangle EDC are right triangles from the definition of a right triangle. So we have to establish that they're right triangles in order to possibly use hypotenuse leg. Then we go down to knowing AC is the bisector of BD. That was just given info again, part of our given. And now they're going to apply that to say that BC is congruent to DC. So BC was congruent to DC from that definition of a bisector, or in this case, segment bisector. Now, if you look at our two triangles, we have a hypotenuse and a leg on each that are congruent. They're both right triangles, so I can now state ABC is congruent to EDC from the hypotenuse leg congruence theorem. And now our last example. Looking at this gate, that's kind of a word scenario, kind of a visual scenario. They want us to state what postulate or theorem could be used to conclude triangle ABC in this image is congruent to EDC. So all my explanation is actually done by marking what I know in the gate picture. So first off, entrance to a ranch has a rectangular gate. Key term there. Rectangular gate tells me my four corners are right angles. So angle B, A, E, and D, all right angles. And then I know side AB is congruent to side DE. And then the whole top, B to D, would also be congruent to the whole bottom, A to E. Just some info we already know. Then, we also know, as it says here, you know that triangle AFC is congruent to EFC. So AFC right here, A to F to C, is congruent to E to F to C. So why does that matter? Well, then I know that CF is congruent to itself, which is the reflexive property, but I also know the key info that CE is congruent to AC. Well, now if I go back to what I have, I knew BA was congruent to DE. I knew AC is congruent to EC, which are the hypotenuses of these right triangles in the upper corners. And I add my right angles. So I have a hypotenuse and a leg plus the right angle. So I could state that ABC is congruent to EDC, this triangle here to this triangle here, by the hypotenuse leg congruence theorem. And again, you can ignore the problem numbers and page number down there. Go with the ones that are posted in Google Classroom, please. So in this lesson, you have two pieces to really keep track of: the hypotenuse leg congruence theorem, as well as the side angle side congruence postulate.